Okay, this is chapter 9.2, angles and radian measures. So the essential question is, how can you find the measure of an angle in radians? And what is a radian? Let the vertex of an angle be at the origin, with one side of the angle on the positive x-axis. The radian measure of the angle is the measure of the intercepted arc length on the circle of radius 1. It's called the unit circle. To convert between degrees and radian measures, use the factor that pi radians divided by 180 degrees equals 1. Okay, so that's just a really brief description. Without diagram, it's a little difficult. What you will learn is how to draw angles in standard position, find coterminal angles, and use radian measures. So let's take a look. Okay, so drawing angles in standard position. In this lesson, you will expand your study of angles to include angles with measures that can be any real numbers. Okay, so positive or negative. All righty. So core concept, angles in standard position. In a coordinate plane, an angle can be formed by fixing one ray called the initial side and rotating the other ray called the terminal side about the vertex. Okay, so the vertex in our case is going to be at the origin. The initial side is going to be laying right on the x-axis, like it said in the prior page. And as you open this angle up and rotate it around, this angle increases in degree. So counterclockwise is positive. An angle is in standard position when its vertex is at the origin and its initial side lies on the positive x-axis, standard position. Okay, so we have an initial side where it began and the terminal side where it opened. So picture a book laying on a table. The back of the book sitting on the table would be the initial side, and the cover at the top of the book is above. As you open the book, that is your terminal side. The measure of an angle is positive when the rotation of its terminal side is counterclockwise and negative when the rotation is clockwise. Okay, so when you open it like this, counterclockwise is positive. All right. Counterclockwise, positive, positive, counterclockwise. Negative when clockwise. The terminal side of an angle can rotate more than 360 degrees. So just like a clock, we can just go around over and over and over, and you increase by multiples of 360 for each full rotation. Okay, so let's take a look at some examples on this new topic. Okay, so here's example 1, drawing angles in standard position. So standard position means we're at the origin. Our initial side, okay, so I'm going to draw that here. So we're going to always have an initial side on the x-axis. So first of all, here's x, okay, and here's y. So I'm just going to label all these. These are for each one. Standard position just means the angle is at the origin and your initial side is the x-axis. So now let me just draw a ray. And let's make it blue. And it's right here. Okay, so there's my initial. Okay, that's by definition. Your initial side is on the x-axis. Okay, let me just move this one up just a smidge. Okay, so that's how you start. The initial side is on the x-axis. And then we're going to rotate around the number of degrees counterclockwise if it's positive. Okay, so in this case, 240 degrees. Well, let me just label this up a little bit. When we go up here, this is 90 degrees, right? This is a 90-degree angle right there. So if I rotate up to here, I'm at 90 degrees. So let me just get rid of that. And then if I rotate over here, we have a straight line. Well, that's 180 degrees. And then if I rotate down around here, 180 plus another 90 is 270 degrees. And rotating all the way around back to the beginning, our initial was 0 degrees, and then we put a comma and we put 360 degrees here. Okay, so that's just to get you started. Those are just the axes, 90, 180, 270, 360. Pretty simple. Okay, and we want to go to 240. Well, 240 is more than 180 and less than 270. So remember, this is quadrant 1, quadrant 2, quadrant 3, and this is quadrant 4. And now this explains why we number them in that order, because now we are going to take and we're going to make another ray. And I'll make this one, I don't know, purple. Okay, so here's my ray here. So I'm going to leave that centered at the origin, like so, and I'm going to rotate it around. So if I rotate this around, here's 90 degrees, here's 180 degrees, and here's 270. So somewhere in between is 240. So what I would do is I would take and subtract 180 from 240, and 14 minus 8 is 6. So I want to go another 60 degrees. So I want to go 180 degrees plus another 60 degrees. So this is 180 degrees to here, and then another 60 to get to 240. Okay, so where is 60 degrees? Well, 45 is right here. Okay, so 60 might be, oh, I don't know, about here. Okay, so there is a total. So now let me just get rid of this here. All right, and let me go back. And so then you would draw an arc around like so, showing which way it opened and how many times it rotated around. So that's not one full rotation. And then that would be 240 degrees. Okay, so that's how you do these. So now let's move on to the others. Let me just give more room. Let me move them over now. Okay, and move this one over here. All right, so the next one is 500 degrees. So again, I'm going to, I already have it there. You have your initial side, and now I want to copy this over and just put it right here. And obviously you can't do this without a computer. If you're doing this on paper, you have to do this by hand first. So let me just set this right there. Okay, so that's a 0 degree angle. The initial and terminal are at the same location. It's either 0 or 100 or 360 or any multiple of 360, depending on how many times it's spun around. So we have 500 degrees. So if I take 360 degrees and I subtract, I get 4, 9, 10, or actually 0, leave that 10, 4, 140 degrees. Okay, so that's more than 90. So then I'm going to subtract that from there and I'm going to get 50. So what that means is I went around, here's 90 degrees, 180, 270, 360, plus 90 is 450. And I want to go 50 more degrees. Well, here's 45 and 5 more. Okay, so that's where the terminal end would be, but I have to show that as rotating around more than once. So what you do is you coil. So here is one full rotation, and we continue around until here. Okay, and that's how you show it. So this would be 90, 180, 270, 360, plus 90 is 450, plus another 50 is 500 degrees. Okay, so this is 500 degrees. And you could also do this. Okay, the book is showing this being 140 degrees, and 140 degrees is how much further than 360 we went. Okay, so there is an angle of 500 degrees. Okay, last one, C, negative 50 degrees. I have my initial side. Let me get a terminal. Move it over here. Set it right on the origin. Rotate it around. There is 0 degrees. Negative 50 degrees means to go counterclockwise. So negative 45 is right here. Negative 50 would be another 5 degrees. I'm just approximating. Okay, and then I would take my, why did that turn red? Okay, I'm going to take my pen now, and I'm going to show it rotating this direction. So clockwise is negative, and then you tell how many degrees it went. Okay, so there are 3 examples of how to show how to draw an angle in standard position. So now you should be able to do problem number 6 and 8 on your exercises. Okay, so now we're going to talk about finding coterminal angles. In example 1b, right here, 1b, the 500-degree angle, right here. In example 1b, the angle 500 degrees and 140 degrees are coterminal because their terminal sides coincide. An angle coterminal with a given angle can be found by adding or subtracting multiples of 360. Okay, so let me go back. So really there are 2 rays here, 2 terminal sides rotating around 1 full rotation or 140 degrees first, and then a 360, so 1 more rotation around after that. So really what you could do is go 140 degrees and then go 360 more, full rotation. Okay, so those 2 sitting on top of each other are coterminal. That's what it means. So example 2 says to find coterminal angles. Find 1 positive angle and 1 negative angle that are coterminal with A, negative 45, and B, 395 degrees. So let me bring in some more grids. Okay, so here we go. So what we're going to do, here's A. This is A. I'm going to rotate this to negative 45 degrees. Okay, so it's halfway between down here. And I want to show that as negative 45 degrees. So I'm going to go like this and draw an arrow and say negative 45 degrees. Okay, so there's the angle that we were told to do. And it says find 1 positive angle and 1 negative angle that are coterminal. So what you're going to do is you say negative 45 degrees plus 360 degrees equals, and I'm just going to put this underneath like this so I can calculate it. So I'm going to get a 5. 10 minus 5 is 5. This is now a 5 minus 4 is 1. So it's 315 degrees. Okay, so 315 degrees. So then what I'm going to do is just simply go this way and show it as 315 positive degrees going in the positive direction. And it's going to land at the same location as this negative 45 degree angle. So those 2 angles are coterminal. And then I need to go the other way. So I'm going to say negative 45 degrees minus 360 degrees is going to equal 5 plus 0 is 5. 4 plus 6 is 10, carry the 1. So that's going to be a negative 405 degrees. So what that means is I'm going to start at my initial side and I'm going to go around like so. Here's 360 degrees. And then I'm going to continue on my second rotation and end up at negative 405 degrees. 360 plus another negative 45 is going to give me negative 405 degrees. Okay, so there's 1 positive coterminal angle and the green negative coterminal angle where I went down 45 degrees, or I should say clockwise 45 degrees, and then an additional 360. Okay, so those are coterminal angles. Now let's look at B, 395 degrees. So what I'm going to do is first explain to you what 395 is. 90, 180, 270, 360, and I want to go another 35 degrees, which would probably be about there. Okay, so that's 395 degrees. I'm going to show that with an arc with what I did. I started at the terminal, at the initial side, went around 1 full rotation for 360, and all the way around a little bit more to 395 degrees. I'll do that in blue. Okay. So then I take the degree measure that I have, 395 degrees, and I'm going to add 360 degrees. and I'm going to take 395 degrees and I'm going to subtract 360 degrees. That's all you have to do to go one rotation beyond. You could do multiples as well, 7, 20, and so on. Okay, so when I add these, 5 plus 0 is 5. 9 plus 6 is 15, carry the 1. 3 plus 3 is 6, plus 1 is 7. I'm going 755 degrees. So let me change this color to the color I'm going to use for my ray, or my arc, I mean. So this was 755 degrees. So I'm going to start here, and I'm going to go around like so. So I could go around like that and then go around again. So that's just one example. 755 degrees is 2 full rotations plus more. Okay. All right. So that's one way to do it. That gets a little messy though. And here's what the book is showing. So then we're going to take, and instead of add 360, we're going to subtract 360 and get 35 degrees. Okay, so then all I'd have to do is go like this direction, and say, oh, that's 35 degrees. Okay, and then I can subtract a multiple of 360. So minus 360 times 2. Okay, and that's going to be 395 degrees minus 360 times 2 is 720. And let's see, 720 minus 395, just to show you, 10, 5, 7 to 6, 11 to 325. And you take the sign of the bigger, that's negative 325 degrees. Okay, so let me change the color of all these to what I'm going to use. And what have I used? I haven't used red, so let's use red. So then I will get my red pen, and I want to go negative 325 degrees. So let's start here. Here's negative 90, negative 180, negative 270, negative 325 degrees. Okay, so that is finding positive and negative coterminal angles. Now you should be able to do problem numbers 10 and 12 on your exercises. Okay, so let's talk about radians now, using radian measure. An angle can also be measured in radians. Let me stop right there. If I turn my calculator on and go to mode, and I arrow down to, here are radians, and then if I arrow over here and hit enter, it'll switch my calculator to degrees. So the calculator will convert from radian to degree. So you can either find an answer in radians or degrees using a calculator, but this is where it comes from. Angles can also be measured in radians. To define a radian, consider a circle with a radius of r. So here's a circle, and as you can see, the distance from here to here is the length r. So radius r, centered at the origin as shown. 1 radian is the measure of an angle in standard position whose terminal side intercepts an arc of length r. So if I took this radius, okay, so let me do this. If I took and created a segment array, and let's make it red. All right, so here I am at the origin. If I took this radius distance like so, and then moved it over to here, okay, and then turned it like so, but bent it so that it formed an arc, then this arc length would equal this. So just picture that getting bent around. And so 1 radian is 1 radius distance of the circumference, if you will. Okay? Because the circumference of a circle is 2 pi r, there are 2 pi radians in a full circle. So degree measures and radian measures are related by the equation 360 degrees equals 2 pi radians, or 180 degrees equals 1 pi radian. Okay, and that's where this comes from. So now core concept says converting between degrees and radians. Simply multiply the degree measure by, to go from degrees to radian, you multiply by pi radians over 180. And to go from radians to degrees, you multiply by that reciprocal 180 degrees over pi radians. Okay, so let's take a look at how to do this with examples. Okay, so now we're going to convert degree measures to radians or radians to degrees. So here is 120 degrees. So what you do is rewrite it as 120 and use the word degrees. Okay, think of that as over 1. Now, if I go back and look at this, you want stuff to cancel. So if degrees is in my numerator, I need to multiply by a fraction where there are degrees in the denominator. So the degrees cancel. So you look at these two possibilities, which one has degrees in the bottom? Well, this one does. So you write 180 radians over 180 degrees. I'm sorry, let's try that again. 1 pi radians over 180 degrees. So you write pi radians divided by 180 degrees. Okay, so what's going to happen here is degrees are going to cancel. Degrees divided by degrees is 1, it cancels. 0 cancels, and 6 will go in, what will go into 12 and 18? It's 6. 6 will go into 12 twice. 6 will go into 18 3 times. Okay, I didn't close my parentheses here. So what do we end up with? We have 2 pi radians over 3. So you just write it as 2/3 or 2 pi over 3, and then you write radians on the outside. Okay, so 100 degrees is 2/3 pi radians. Okay, and that's how you do it. It's actually quite simple. So let's do another one. This one, we have it in terms of pi. So first, write the problem as negative pi over 12, but pi is degrees, or I mean radians. So this is in radians, this is in degrees. So since this is in radians, I want to write radians. I'll put it in the numerator. I'll put radians up here, like so, and then I'll do my parentheses. And this time I want radians in the bottom. So pi radians is going to go in the denominator. And my numerator is going to be 180 degrees. Oops, I don't want degrees, and I did that in the last one too. So get rid of that little thing there and get rid of that there, and just write the word out. Okay, so again, radians will cancel radians. Pi will cancel pi. And 12 divided by 180. This could be, will 12 go into 18 one time with a remainder of 6? So that'd be 5. So 12 turns 180 into 15, right? Or if you want to use your calculator, all you have to do is go 180 divided by 12 is 15. Okay, so negative pi, and there's a negative sign right here. Don't miss that. So my answer is going to be negative 15 degrees. Okay, and that's how you convert between degrees and radians. Hopefully that makes sense to you. Practice problems are 14, 16, and 18 in your exercises. Okay, so now we're on to a concept summary, degree and radian measures of special angles. Okay, so don't get too intimidated by this. It's just simply a circle. And if you look at the inside, you should already be familiar with degree measures. Here's 30, here's 45, 60, 90. So we're using special right triangles here. So in geometry, we learned the 30, 60, 90 triangle and a 45, 45, 90 triangle, and that's where these values come from. And then you just simply repeat yourself in every quadrant. So 30 degrees, 45, 60, 90, 30 degrees more than 90 is 120, 45 degrees more than 90 is 135, and 60 degrees more than 90 is 150. Then you go on to 180. Add 30 210, add 45, 225, add 60, 240. So you're just adding 30, 45, and 60 in each quadrant. So it's just repeats itself actually. So if you learn the first quadrant and just add 90 to it, you got the rest. Add 90 and add a 90 again and add 90 again, of course. Now when we switch to radians, 30 degrees is pi over 6. So how did they get that? Well, if we say 30 degrees over 1 and we multiply it by 180 degrees in the denominator, see, it's really easy. You put the 180 degrees in the other location. So if degrees is in the numerator, you put 180 degrees in the denominator, and that is pi radians in the numerator. So the degrees cancel. Okay. 30 goes into 18 6 times, and therefore you get pi over 6 radians. And that's where these come from. So it's really not that difficult. Hopefully you just get your head around that and figure it out, and maybe practice these to see if you get these values. All right. So anyway, so there they are, pi over 6, pi over 4, pi over 3, pi over 2, but then it goes to 2 pi over 3. Well, again, double that. That's 4 pi over 6. So think of this as 1 pi over 6, 1 pi over 4, 1 pi over 3, pi over 2. And then this becomes 4 pi over 6, 6 pi over 8, and so on and so on and so on. If we multiplied these up to get the same denominator, it'd be 1, 2, and so on and so on and so on. So you may find it helpful to memorize the equivalent degree and radian measures of special angles in the first quadrant, and for 90 degrees, pi over 2 radians. All other special angles shown are multiples of these angles, as I said. So let's take a look at that. Okay, so now we're going to talk about a sector. A sector is a region of a circle that is bounded by 2 radii and an arc of the circle. So think of a whole pizza. You cut one slice out. That is a sector. Okay, the sector is the area of a circle between 2 given radii, and the arc length S is the length of the sector. So arc length and area of a sector. The arc length S and area A of a sector with radius R and central angle theta measured in radians are as follows. Arc length S equals radians times theta, in other words, times the angle. Okay, arc length, the arc length S is the length of the radius times the angle measured. The area is 1/2 radius squared times the central angle. Okay, so let's take a look at that in examples. Okay, so here's example 4, modeling with mathematics. A softball field forms a sector with dimensions shown. So a sector is an area. So it's an area so the ball field is an area. So where the outfield fence is the portion of the radius, or I'm sorry, the circumference. That's the outside of the circle. The home plate is our vertex, our angle of center of the circle. And it says find the length of the outfield fence and the area of the field. Now, remember, if we go back here, the important concept here, the important thing you need to know is when we're talking arc length and area of a sector is measured in radians. So the first thing we have to do is convert degrees to radians. So here's 90 degrees. Okay. So I want to convert that to 90 degrees. So convert 90 degrees to radians. So 90 degrees over 1 times 180 degrees in the denominator over pi radians. Okay, degrees cancel. 90, 180 becomes 2, and we get pi over 2, and then I can put radians outside. So it's pi over 2 radians. So 90 degrees is pi over 2, and if you remember, or if you go back, Here it is, 90 degrees is pi over 2. Okay. All right, so what next? Well, the first thing you have to do is understand the problem. You're given the dimensions of the softball field, 200 feet in a straight line down the first base line to the fence, and 200 feet down the third base line to the fence are equal, forming a quarter circle, a semicircle, half of a half circle. All right, and the distance, the radius r is, switch back to my pen. I thought I already had pen. R equals 200. Okay, so that's our radius of our circle in this case. That's our radius. So we now know that the central angle, and what is the central angle called? Theta. So let me erase that circle there. So that is my theta. So I have theta equals this pi over 2 radians. All right. Let me just do this. Let me move this over so they line up. And these are what we need. So you need to know what theta is, and you need to know what r is. So that's the first thing we do. Theta is pi over 2 radians, and r is 200. So understand the problem. You're given the dimensions of the softball field. You're asked to find the length of the outfield fence. That is right here. And what's that called? That's called the arc length. And then you're asked to find the area of the field, which is the area of the sector. So that's what we're trying to do here. Next step, make a plan. Find the measure of the central angle in radians. I've done that. Okay, pi over 2 radians. Then use the arc length and area of a sector formulas, which I brought in, they're right here, and solve the problem. So here we go. So we have the pi over 2 radians. So arc length, we're going to find that first. They asked for the arc length, the length of the outfield fence. Arc length equals, write a formula, or not equals. Let's just say arc length S. So here's arc length, and we're going to represent that as S equals R theta. So arc length, which is S, equals R 200 times theta, which is pi over 2. Okay, well, the 200 divided by 2 is 100, so that's going to be 100 pi. All right, 100 pi. And what is 100 pi? So when you go to your calculator, well, I don't even need my calculator, it's times 100. Remember, pi is no, that was an approximation. As soon as I get rid of pi, I have to write approximately. So now S is approximately 100 times 3.14. Okay, pi is 3.14, and multiplying by 100 moves it over 2 decimal places. So the length of the fence is approximately 314 feet. Okay, so there's arc length or the outfield fence. The next thing we want to do is area of the sector. So area is going to be, let's use purple. A equals 1/2 R squared theta. Write the formula, substitute the givens. R is 200 squared times pi over 2 radians. Okay, so area equals 1/2. Remember your order of operations, PEMDAS, parentheses, can't do anything inside the parentheses, exponent 200 squared is 4,000. I'm just showing all my work. Okay, so it's 1/2 times 4,000, or is it 40,000? 2 times 2 is 4, and 4 zeros, 40,000. And then times pi divided by 2 radians. Okay, well, 1/2 times pi over 2 is 1/4, right? So now I have a 4 in the denominator that I cancel this 4. So these halves in the denominator will become quarter. 1/2 times pi over 2 is pi over 4. And the 40,000 divided by 4 is 10,000. Okay. And pi radians. So the area equals, remember pi, and I did it again. As soon as you go from pi to an approximation, you need to approximate with a symbol, and that will be 10,000 times 3.14. Okay. All right. So moving that decimal place, multiplying that by 10,000 moves it 1, 2, 3, 4 places. So the area is approximately 3, 1. So 1 decimal place, 2 decimal places, 3 decimal places, 4 decimal places, and it's approximately 31,400 feet squared. Okay. And the book shows 31,416. They just took pi out that many decimal places. 3.14159 rounds to 16. So they have 31,416 square feet. So I just rounded it sooner. And that's how you do this. So now you should be able to do problem number 27 in your exercises. Okay, so that brings us to the end of chapter 9.2. Hopefully you understand a little more about the unit circle and radians and degrees. These are the exercise problems I assigned. Thanks for watching and have a great day.